Welcome back to Calculus 1. Up to this point, we have relied on informal, intuitive phrases to describe limits. We used words like getting closer and closer to, aiming at, or tracking the path. While these intuitive concepts are excellent for building foundational understanding, they are far too ambiguous for a rigorous mathematical framework. What exactly does close mean? How close is close enough? In the 19th century, mathematicians realized that calculus required a more foundationally secure, precise definition to survive intense scrutiny. This realization birthed the formal definition of a limit, universally known as the Epsilon-Delta definition. This definition abandons vague, intuitive phrases and replaces them with strict, quantifiable inequalities. Mastering this definition is the true rite of passage for any serious student of mathematics, transitioning you from mere calculation to rigorous logical proof. Let's dissect the core vocabulary of this new language. The definition revolves around two Greek letters, epsilon and delta. First, epsilon. In mathematics, epsilon universally represents an infinitesimally small positive number. Specifically, in our definition, epsilon dictates the maximum allowed error tolerance on the y-axis, the outputs. It essentially asks a purely theoretical question. Can we guarantee the function's output stays within a tiny epsilon-sized window tightly packed around our target limit L? Delta, on the other hand, also represents a small positive number, but it operates on the x-axis, the inputs. Delta is the answer to epsilon's challenge. It dictates how tightly we must control our x values around our target point, A, in order to successfully force the resulting y values to stay trapped inside epsilon's window. If epsilon is the boss setting the strict manufacturing tolerance, delta is the machinist determining exactly how tight the calibration must be to achieve it. With this vocabulary, we can now state the formal definition. We write, the limit of f of x as x approaches a equals L if and only if, for every epsilon strictly greater than 0, there exists a tightly corresponding delta strictly greater than 0 such that the following logical implication holds true. If the absolute value of x minus a is strictly bounded between 0 and delta, then it absolutely must guarantee that the absolute value of f of x minus L is strictly less than epsilon. This is a profound, dense mathematical sentence. Let's break it down. The condition absolute value of x minus a is less than delta simply translates to x is horizontally within delta units of a. The condition absolute value of f of x minus L is less than epsilon translates to the output height is vertically within epsilon units of L. The entire structure is a powerful, inescapable if-then guarantee. To truly internalize this massive statement, we must visualize it. Imagine a coordinate plane with a generic curve. Let's locate our target x value and target limit height L. First, imagine we are handed an arbitrary random epsilon by an opponent. Visually, we draw a horizontal band across the graph. The top of the band is at L plus epsilon, and the bottom is at L minus epsilon. This is our target survival zone. Now, the burden of proof falls on us. We must find a delta value. Visually, we drop down to the x-axis and draw a vertical band. This band spans from A minus delta to A plus delta. Our mission is successful if, and only if, every single piece of the curve that falls inside our vertical delta column is also perfectly trapped entirely within the horizontal epsilon band. If the curve escapes the top or bottom of the epsilon band, our delta was too wide and we fail. The magic of the true limit is that no matter how mercilessly tiny the opponent makes the epsilon band, we can always find an even tinier delta column to successfully trap the curve. Let's apply this massive logical machinery to prove a simple limit formally. Consider, prove that the limit of the linear function tox plus 1 as x approaches 3 is exactly 7. The opponent hands us an arbitrary epsilon greater than 0. Our goal is to find a specific delta blueprint. We start with the desired conclusion. We need the absolute value of f of x minus L to be less than epsilon. Substituting our functions, we need the absolute value of the quantity 2x plus 1 minus 7 to be less than epsilon. Simplifying inside the absolute value gives us the absolute value of 2 tox minus 6 is less than epsilon. We geometrically factor out the 2, leaving 2 times the absolute value of x minus 3 is less than epsilon. Finally, dividing by 2 yields, the absolute value of x minus 3 is strictly less than epsilon over 2, and there it is. This crucial piece, the absolute value of x minus 3, exactly aligns with our starting delta condition. We have found our blueprint. We set delta exactly equal to epsilon divided by 2. If the opponent demands an error of 0.1, we simply restrict our x values to within 0.05 of 3. Our proof is rigorous, ironclad, and mathematically perfect.